Well, we're going to look at light here. So this is what we're going to start out with. All light is made of waves. So we've got a nice, long, red wave here. Okay? And we call the distance between the top of the wave to the top of another wave the wavelength. So this wavelength, which we use the letter lambda, the Greek letter lambda, this has a nice long wavelength. And to illustrate this, I need a volunteer. So I need a tall volunteer, somebody from the class here who's tall. All right, come on up here. And this is what I want you to do. I want you to stand by this wave and show us how it goes. So put your head about where this line is and go up and down and up and down and up and down, all the way over to the other end, okay?
Okay.
All right. Come on, down, all the way down, all the way down. There we go. All the way down. Good. Perfect. Good. Great. Okay. You can stay right there. Nice job. Well, this is a pretty long wave. Let's do a shorter wave. So here's a green wave that's a little bit shorter, has a little shorter wavelength. Okay. And you can see that has a little bit shorter wavelength. If we make a line from the top again to the top of the next one, that wavelength, that green wavelength, is a little bit shorter. And so I need a medium-sized volunteer here. So, okay. So you come on over here. You need to do the same thing as she did, but follow the green wavelength. All the way down, all the way down. There we go. Up and down, up and down, and up and down, up and down. Okay. So that's the medium wavelength. Okay. Now let's make a really short wavelength. Okay. So here we go. This is a purple wave. Up and down and up and down. Nice small wavelength here. Okay. You can see that this wavelength here, lambda, is quite short from here to here. So now we need a tiny volunteer. So come on up. You got to do the same thing here.
Okay. So,
there you go. That's it. Oh, you're doing great. That's good. That's good. Very good. Tiny wavelength. Good. Oh, hey, very good. I wonder enough now. So all light travels at the same speed. So light has different wavelengths. Different colors have different wavelengths. But all light travels at the same speed. And that's called the speed of light, right? The speed of light. So you guys are all going to travel at the speed of light, 186,000 miles per second. Not really. All together, same speed, right? Shoulder to shoulder, but going up and down with the different wavelengths that you went for before, all right? Well, let's see if you can do it. All right. Shoulder to shoulder, all three at the same time, all at the same speed. Shoulder to shoulder, stay nice and close. All right, here we go. Ready? Go. Follow your line. There you go. There you go. Stay together, because you're at the same speed, the speed of light. Stay the same. Right, it's hard. All right, very good. Nice job, ladies. Good. All right, you can go back now. Nice job, nice job. So you can see that different wavelengths of light exist, okay? The light that we can see is called visible light, okay? So this is visible light. And visible light has a wavelength, how long it is, this lambda, from about 400 to about 700 nanometers, okay? About 400 to 700 nanometers, okay? There's light that's even shorter than this, from about 200 to 400 nanometers. A nanometer is a billionth of a meter, so it's very, very, very small. From 200 to 400 is smaller wavelengths. The largest wavelengths are the red wavelengths, just like we have here. The smallest wavelengths are the purple wavelengths, so they're down here. Well, purple or violet wavelengths. So the wavelengths that are even smaller than the violet are called the, come on, you know this, Smaller than violet are called the ultraviolet, right? The ultraviolet wavelengths. So these are the UV or the ultraviolet wavelengths, okay? Well, bigger than the red wavelengths from maybe 700 nanometers way up to maybe in the 2000 nanometer range, okay? This has above the red, ever hear of this word? Come on, you can come up with this. This is called the infrared, right? So this is the IR region, and this is the region that's going to be really important for us for climate change, okay? So far, so good? A couple other quick things we're going to talk about. We've already talked about wavelength, okay? But there's also a term called frequency. Okay? I'm going to write that word here, frequency. Okay. So wavelength we've got. Frequency is how often these waves come by a point. So think of these waves as moving towards me, okay? So as the waves move toward me, which color will be the most frequently hitting me? Can you think of that? So think about waves hitting me. Which is going to hit me? What's the purple one, the violet one, right? Okay, so it is the most frequent. It has the highest frequency. Okay, so the purple has the highest frequency. Okay, the purple has the highest frequency. So the longer the wavelength, what happens to the frequency? The longer the wavelength, the shorter the frequency, right? Now, there's one other thing we need to know, and that's about energy. And light has energy. You know that because, you know, you get sunburn, right? Light has energy. Okay, which of the three people here had the most energy? Who had to put in the most energy? The purple one. The person who had to move up and down the most had the most energy, all right? So that means that energy, the most energy, has the shortest wavelength. The shortest wavelength has the highest energy and the highest frequency, right? So the higher the frequency, the higher energy, okay? So this is all about light, and we're going to look a little bit further into other parts of light in the next part we're going to take. So that's it, guys.